I'll try to use this because I never keep the hand mic at the right distance from my mouth, if you know what I mean. First of all, I have to say I'm jealous of the 20 or so people who are asleep. I wish I were too, having just flown in. I'll try to keep you awake in any event with some comments here. I want to talk about desalination, which has been my interest for some time. In particular, we've been looking at desalination as a problem in thermodynamic systems analysis. And I'd like to explain to you why that is and what we see as some of the opportunities and ideas and perhaps low-hanging fruit that comes around the problem of energy-efficient desalination as a result. I think for this audience, the next slide is pretty straightforward. This is some data assembled by Oki, which shows net precipitation over land divided into water withdrawal for human use. The areas in red are using essentially 100% of their renewable supply of fresh water, which is net precipitation over land. And I put this up simply to make the point that water scarcity is very widespread. It's in places that you might not expect, very wet areas as well as very dry areas, rich countries, poor countries, etc. And certainly a major driver of this is the fact that the world's population has grown so much and is continuing to grow. I'm showing here a couple of benchmarks. 1927, we had about 2 billion people in the world. Current forecasts are that we'll have 9.6 or 9.7 billion in 2050, which is to say that over a period of a little more than 120 years, the world's population will have gone up by a factor of 5. Which means an additional 8 billion people obtaining their fresh water from the same more or less fixed source, which is net precipitation over land. So this strain is at the root of the chart I showed you before. Beyond that, when you start thinking about heavily populated areas and what happens when there's climate variability and fluctuations in weather, perhaps something as simple as a drought, you wind up with a situation such as shown here. This is one of the major reservoirs serving Sao Paulo, which is among the world's largest cities. They had a 4-year drought, and their reservoirs by spring of 2015 looked about like this. You can imagine a city of 20 or 30 million people going on water rationing, but that's about the point they were. And my point being that when you have these very high population densities, urban resilience to fluctuations in water supply is much lower. The result of this is that many places, Singapore included, have been looking very closely at seawater and groundwater desalination as a means of providing some additional baseload capability in their water networks. In this particular instance, I'm showing photographs of a plant that just opened in San Diego, California, or more specifically in Carlsbad, which is slightly north of San Diego. This is the largest desalination plant in the Western Hemisphere at this point. North America has been somewhat slower to adopt desalination on a large scale. What you can see also in my numbers, the energy requirements here for the RO stage alone are about 2.7 kilowatt hours per cubic meter for desalination. That's electrical work that's being provided. When you account for intake, supply, outfall pumping, high pressure service, and so forth, the entire plant is actually consuming about 3.6 kilowatt hours per cubic meter. Desalination has a reputation of being very energy intensive, and these numbers give you some sense of what that means when you are working at the state of the art today. If I had put up similar numbers in 1970, they would have been 7 times higher than this for reverse osmosis plant. So there really has been considerable improvement in the technology on many fronts over time. But still, it remains energy intensive. At the end, though, what you're concerned about is not just the energy, but it's also the cost of water. You will make a decision of whether or not to adopt a new solution for your water supply on the basis of how many dollars per cubic meter the water will cost you relative to other resources that might be available. So this chart shows some representative numbers. I'll emphasize there's significant variability from plant to plant and case to case. But what you see is that energy represents, in this case, about 1/3 of the total cost of water. A lot of the rest of the cost is coming directly from the capital investment that goes with the plant, buying the land, buying the facilities, getting it built, paying the finance financing, depending on how you finance the plant. And below this, I'm showing some breakdown of the CapEx of the plant. At the top of the list, accounting for almost a quarter of it, is piping, pumping, high-pressure service for the plant. It's really the fact that you've got to take seawater to a pressure of around 60 or 70 bar behind the membranes in order to get it over the osmotic pressure at the ends of the modules. It's the fact that you've got to drive that high pressure that makes seawater reverse osmosis as energy intensive as it is. The drive to lower that then is to find ways to lower the pressure. But you'll notice as well that the cost of water is really heavily affected by how much of that high pressure service you need and how many of these high pressure pipes you need. When you look at the list of drivers of CapEx, the membranes per se are actually a fairly small fraction of the total cost. And so from my perspective as a mechanical engineer, this looks more and more like a problem in hydraulics. Of course, it's a problem in separations as well, but very much a problem that is not simply about finding a new polymer surface for a seawater desalination membrane. Now, as a mechanical engineer and a person with a thermodynamic background, when I look at a plant like this, what I see is a control volume like this. It's perhaps an engineer's disease, but everything I look at becomes a control volume pretty soon. So from my perspective, this desalination plant is a stream of seawater coming into a control volume. Out of this control volume comes a stream of pure water and a stream of highly saline brine. How saline? It's about twice the salinity of the incoming water. You've recovered about half the incoming seawater as fresh water. Now what you've done here is you've unmixed. You had a separation process. You provided the work of separation to remove water from salt water. You've raised, if you like, its chemical potential relative to where it was. And to do that, you had to provide work in a thermodynamic sense, or more specifically, you had to provide the electricity to drive the pumps in the system. It's a straightforward exercise in the first and second law of thermodynamics to analyze the best case scenario. You simply assume that the system is reversible, that there are no losses. First and second law calculations tell you that if you're recovering 50% of the water from seawater, the best you will ever do is to need about 1 kilowatt hour of electricity per cubic meter. You're not going to beat that. And that's a fact that, on one level seems very obvious, but on another level, I am about once a year confronted with a paper, a technology, a startup that claims to go well below that limit. And so the thermodynamics is not always properly embedded. Now, as I showed you in the Carlsbad plant, today's plants are running at something like 2 to 4 times the reversible limit. And they do that because real plants have losses. There is friction. There are separated zones in the pumps. There is irreversibility as water is driven through membranes at high pressure. And all of that, from my perspective as a thermodynamicist, is accounted for by something we call entropy generation. It's the creation of entropy as a result of these irreversibilities. The design problem, from my perspective, is to minimize entropy generation and to make a more reversible plant. Now, to give you an illustration of where these losses arise, I'm showing in the upper part of this a flow path through a typical pressure vessel in a reverse osmosis plant. If you recall the photograph I showed you of the Carlsbad plant, there are all those big white pressure vessels. So this is a spiral wound membrane module inside one of those vessels. Seawater enters at high pressure and gradually fresh water flows out, the blue stream here, through the membranes, with a more concentrated brine being left behind, not having passed through the membranes. The process of getting water to flow through the membranes is to provide a hydraulic pressure that exceeds the osmotic pressure of the water locally. The osmotic pressure is highest where the salinity is highest. The salinity is highest at the outlet of the module where you have the brine. And therefore, the incoming water is pressurized to a hydraulic pressure above the outlet brine osmotic pressure. In other words, it's greatly overpressured over much of its length. The irreversibility that results goes roughly as the square of that pressure difference, and as you can see on my chart here, you get a lot of irreversibility near the left-hand side of that graph, where the pressures are much too high. Now, from a design perspective, what might you do? Well, one simple thing to do would be to go to a double pump arrangement, pump it up to, say, 40 bar, and let the water flow until the osmotic pressure is 38 bar, and then repressurize with the second pump to 70 bar, and then let the rest go through. The problem with that is that you pay for it in CapEx, because the large pumps are expensive, they're high capacity, they're high pressure. These things are not cheap. The pump in Carlsbad is a 6,000 megawatt pump, just to give you a sense of size. Rather big. There is another way to do this, though. We're working here with a variation in the salinity of the seawater in the streamwise direction. Suppose that we replace the physical displacement, the distance, the streamwise position, with a time variation. And imagine instead that you gradually raise the pressure next to a membrane as the salinity of a charge increases. And so you might have a batch process like this, where you fill the pressure vessel with a piston with an initial charge, turn off the pump, and then gradually raise the pressure as water flows out through the membrane module, thereby never taking the hydraulic pressure much above the osmotic pressure. There have been semi-batch designs. In fact, some of them are commercial. We recently came up with a fully batch design, which saves about 60% of the energy under some conditions. In fact, this work has been patented, and somebody is eagerly trying to license it from us. You see similar ideas in the thermal processes. I should say, someone was asking me over lunch, where are thermal processes in this spectrum of desalination? Thermal desalination is almost always less energy efficient than membrane desalination for seawater. And the reason for that is that you design systems around CapEx. If you wanted the thermal systems to be really energy efficient, you'd need to use very large heat exchangers with very low temperature differences, which means a lot of very expensive copper alloy tubing. The water would be too expensive, so people don't design them for energy. They design toward dollars per cubic meter. But this is an example of an evaporative desalination process, a very simple thing. Imagine a cooling tower, right? You've got warm water coming in over a splash packing. You've got entering the bottom, say, cool, dry air. The air rises, water evaporates into it as the water stream goes countercurrent. The air leaving the top of the cooling tower is now warm and humid. And it contains pure water because the salts don't vaporize. So you've separated pure water from saline water by that process. As it happens, you've changed the enthalpies of both of these streams. You've changed the enthalpy of the seawater stream by cooling it off, essentially lowering its temperature. It's a one-parameter problem. You've also raised the enthalpy of the air stream by warming it and humidifying it. It's a two-parameter problem, so it's a little more complicated than a simple heat exchanger. But it turns out that if you look at the ratio of the enthalpies change for each of these two streams, you can do an analysis and find that when the enthalpy changes are matched, you minimize the entropy generation in a component like that. We've used these ideas to make evaporative and dehumidifying systems that have about 4 times the energy efficiency of what was in the literature for such configurations before we started. Beyond the simple thermodynamic calculation, oh, the video's running. We were struggling with that just before. We've also looked at how you might dehumidify the air when it comes out of the cooling tower. And so what we're illustrating on this chart, you have, say, humid air entering here through a series of water pools at different temperatures. Every time the air passes through a pool, if the pool is relatively cold, some moisture condenses against the surface of the bubbles here. And so water leaving the first pool is less humid and cooler than the water entering. And the same is true progressively as you go on up each stage. So we've managed now to find a way to do the dehumidification at a series of condensing temperatures. The reason that's significant is because condensation essentially occurs at whatever saturation temperature you've got. And if you just pick one pool and did this with one pool, you would give up all the temperature differences in that one stage. And by doing it this way, we have a series of sequential condensation temperatures. We're able to use relatively low temperature differences in each stage, and thus conserve the potential and affect a much larger temperature change in each of the streams. But the second thing that a device like this does, it's direct contact. Right? There's no metal condenser surface. Think about the dehumidifier you might put into your house if it were too humid. It's got a whole bunch of metal sheet in it, little plates, that are in there to reduce the resistance to condensation that comes because air doesn't condense, only the vapor condenses. In this case, we don't need all that metal because the bubble surfaces are constantly renewing themselves. In fact, we've measured heat transfer coefficients in these systems that are comparable to what you would get in pool boiling. So it's got a very low thermal resistance, a very low resistance to mass transfer, and it's staged. The energy efficiency is great, it's compact, it's inexpensive, and the students who worked on this actually commercialized the technology. Now, this is also an interesting point. Thermal technology is not really competitive for seawater in most cases, but when you go to water such as they're looking at here, water from oil and gas production out in West Texas, that water is perhaps 5 times as salty as seawater. The osmotic pressures are much too high for any reverse osmosis system or membranes that are available today, which means that thermal technologies have a very specific advantage in that market. Now, another example of these kinds of analogies between desalination processes and standard thermal engineering ideas is found when you go to look at the membranes and you say, how much membrane area do I need? How am I going to size the membrane module? So in this case, we've sort of unwound one of these spiral modules so you can see the membranes in it. One module like this might be about 1 meter high. It might be 20 centimeters in diameter. It would contain approximately 38 square meters of membrane. And if you recall the photo I showed you of the plant at Carlsbad, a plant like that might have one pressure vessel containing 7 or 8 of those modules and thousands of pressure vessels. The membrane areas are vast, and sizing it is very important. In the heat exchanger literature, there are classical techniques for sizing and rating. Those of you with a mechanical engineering background will recognize this chart instantly. It's an epsilon NTU graph for a counterflow heat exchanger. What do I have here? The effectiveness on the ordinate of this chart is the percentage of total possible heat transfer that a particular device, particular configuration is giving you. The abscissa on this chart, the so-called number of transfer units, is a dimensionless area. It's effectively a sizing of the heat exchanger. And the key point here is that if you undersize the device, the NTU is too low, you're not achieving anything close to the potential heat transfer in that unit. And if you go way out here and oversize it, you're putting in a lot of membrane area that's not doing a great deal for you. So it'd be very nice to have a similar analogy for osmotic mass exchangers like reverse osmosis plants. And we've actually developed this type of an analogy. I won't take you through all the technicalities of it, but you can see here we have a quantity, a number of mass transfer units, like a number of heat transfer units, which is essentially a dimensionless membrane area. We have an effectiveness, how much of potential mass transfer are you achieving, and then some parameters that characterize it. And so we've developed and applied this notion of an MTU for pressure retarded osmosis, reverse osmosis, assisted forward osmosis, the whole category of mass exchangers of this type. So that there are a number of things that can be done just by bringing these techniques over. It's also interesting in this chart that we've got a couple of comparisons. There's some DNS models for an RO membrane module. There are also some analytical models that we did. We adapted some standard ideas about variable wall heat transfer and variable wall heat flux to the conditions you find inside a reverse osmosis module. We were able to do an analytical model, essentially an integral, that allows us to predict what the DNS is telling us is happening. The other point that I'd like to make here is just about permeability and reduced energy consumption. As I mentioned, you hear a lot about novel technologies that are going to change the world for desalination. And several years ago, there were a number of news reports that came out about the new graphene nanoporous membranes and what they might accomplish. This is an example of one that ran in the AICHE's newsletter, stating that graphene desalination membranes were going to require 100 times less energy than conventional reverse osmosis. Quick quiz, is that true or false? be brave. Yes, false, absolutely false, based on what I told you before. We're already within a factor of 2 or 3 of the reversible limit. There's no way you can go a factor of 100 below where we are now, violate the laws of thermodynamics. The problem here, the confusion, you're looking at the permeability of the membrane, not the energy consumption. They're 2 different processes. And so the permeability is about how much water flows through the membrane under a given pressure. But you only have a certain amount of potential to drive water through. And as you give that up, you lose the ability to pass water. So you can't make that gain. You can run at lower pressure, but only for some distance. And in fact, we did this analysis. We went back and looked at the impact of improved permeability on energy consumption for seawater and for brackish water. So this is the membrane's permeability here. Today's reverse osmosis membranes are roughly where that dot is. This is the pressure that you need to apply to produce a given volume of water for a vessel of a given size. And what we find is that the pressure can be reduced for seawater by an amount on the order of about 15%, and that you only need to raise the permeability by about a factor of 3 to get that gain. All of this factor of 100 in permeability is not doing anything for you from a pressure viewpoint, and the pressure simply tracks the energy consumption. So the potential of these novel membranes to save energy is really not as high as what's been built. You can, however, make a much more compact system, and so there are opportunities to save size. The last thing I'll mention, you often hear mechanical engineers talking about isentropic efficiency, efficiency of a turbine, the efficiency of a pump. It's a comparison of where you are with respect to what would happen if your device ran reversibly. If your pump had no losses, you'd run at 100% of the reversible energy required to pressurize a stream. Most pumps don't run at that level. The best available, the big ones they're using in desal plants, might get to 89% isentropic efficiency. Most smaller pumps don't get there. But you can do the same calculation for desalination plants of all types. And so what I'm showing here is the least energy, the least exergy of separating water from salt water, divided by what you actually had to provide in order to do the desalination process. So for reverse osmosis, that would be all electrical work, the 3 kilowatt hours divided into the 1, about 30%. For the thermal systems, you have heat energy that's coming in at some temperature, a high temperature and a low temperature are present, and you also actually have a lot of electricity to drive the pumps in the big thermal plants. So you need a mixed input. But this chart shows the efficiencies over a range of salinities running from over here, seawater salinities, over here, brackish groundwater salinities. What you see is that these systems are running at only 30% of the isentropic limit at best. For the groundwater systems, the low salinity systems, it might be 10%. And so when you consider that a well-designed power plant, combined cycle power plant might be operating at 60, 65% of its potential efficiency, you can see there's a lot of room for improvement at these desalination plants. So that's a rough sketch of things. We're going to be working going forward with the Singapore Membrane Technology Center with Professor Rong Wang, Professor Ziggy Chung, looking at the application of nanofiltration membranes to improving the performance of reverse osmosis plants. We'll be working collaboratively with Eric on some issues about brine discharge as well, and seeing what we can do to minimize those impacts. I think I probably overran my time. I apologize for that, and I'll blame it on myself. Thank you. Yeah.
Any question? We can entertain one question. Okay. Oh.
So how close will you come to the how close will you come to the thermodynamic limit within the next 10 years?
Within the next 10 years. I think I'm always reluctant to be a futurist. I have seen demonstration technology that can reach about a factor of 2 of the thermodynamic limit, which is to say an isentropic efficiency of 50% or so. I've seen model systems that can do better, but which have not been built. One very important consideration, which I didn't mention, I probably should have, is because these plants are being designed around cost of water rather than energy efficiency, the most energy efficient designs are not the ones that get built because they're too expensive. And so the real engineering challenge is to move the cost-effective design up to those limits. So.